last week we had essentially looked at the equation of motion in and finished looking at it in 3 coordinate systems: the x, y, nt, and the r theta coordinate, right? So I know कि मैंने r theta की कुछ examples छोड़ दी थी. We'd just done about 2 or maybe 3. I'm not quite sure. But then I was hoping that you guys would go over them, or अगर कोई query हो तो फिर we can discuss it. So just I want to first ask अगर if somebody has any questions which are still remaining from the last time, we can discuss them now. वरना I think अब because हम DL पे चले जाएं, we're going on to DL mode, and then there's also हमारे mids postpone हो गए हैं, so hopefully we'll have more time. So what we can do is कि somewhere in between we can just arrange a lecture or a sort of time meeting slot just कि we can just discuss some examples. कोई भी जो पीछे से रह गई हो, किसी ने कोई assignment की हो, उनको कुछ उससे समझ ना आ रहा हो, and so on and so forth. So I just wanted to leave that out there कि आप लोग जब भी कोई questions कर रहे हो वो ना समझा रहे हो, so put a little star next to it and do message me and ask me, or we'll arrange a session just where we can deal with all of it. Right. So for today then, still waiting कि अगर कोई किसी ने कोई वाकई पूछना हो, so we can ask right now.
मैम आवाज ठीक नहीं आ रही आपकी.
आवाज ठीक नहीं आ रही.
मैम आपकी आवाज ठीक नहीं आ रही.
अभी कुछ any better या no?
Yes ma'am, better.
Okay, so the internet I think at my end. Asad, just let me know जब खराब हो रही हो. I hope कि अभी ठीक है. तो I was just asking कि kinetics equation of motion in r theta coordinates में से वो जो examples रह गई थी, did anyone try them, and if so, do you have any questions from them? Maybe nobody tried them. But in any case, we've done a few, so hopefully we've hit the ball rolling, and then after that you guys can do some of your stuff. Okay, so today I want to move to a new topic. Just before I move to the new topic, let me just check. Asad, आवाज ठीक आ रही है अभी या अभी भी खराब आ रही है?
Yes ma'am, ठीक आ रही है
अब ठीक है. Okay, चलिए फिर let's jump in. Right, तो अभी भी we're still looking at kinetics, but last week we looked at the equation of motion, right? We'd seen this thing, summation F is equals to MA, the equation of motion. And we'd used this to analyze various different problems. And essentially what we were doing is, was that we were relating how the resultant force on an object can tell us what the acceleration on it would be, right? Now, there is also another way actually, or another method to perform a kinetic analysis of a particle. By kinetic, I mean when we're looking at the cause, the forces or the moments which are causing the motion and the motion simultaneously. And this other way of analysis, kinetic analysis, is using the principle of work and energy. Today we'll see what this is, what this new sort of second method is for kinetic analysis. As always, this is now taken from these sections in Hibbler, so it's chapter 14 that we're starting today. Okay, so today what we're going to be discussing, I just want to bring it up, is we're going to be looking at what the work of a force is, and then from that, once you've described in detail what work is, to look at the principle of work and energy. So there are a few sort of objectives of why we're looking at this. But I'll come to these objectives later. Or I just want to focus on कि आज हम इन दो चीजों पे focus कर रहे होंगे. We're going to be looking at the work of a force and the principle of work and energy to see कि how we can use these two, the work and energy, to solve to perform kinetic analysis. So as we just discussed previously, we've been looking at the equation of motion. We were relating to the force, the resultant force, to the acceleration of an object. But there's actually another way, which is this work and energy method, in which we can actually relate our resultant forces directly to the velocity and displacement of the motion. Okay? तो मतलब ये कि we skip this part. पहले तो हम ये करते थे ना force से acceleration निकालते थे, फिर acceleration से हम kinematic use करके velocity and displacements निकाल रहे होते थे. But in this case, when we use the method of work and energy, we can actually directly analyze force and the velocity and displacement that it causes in a mass. So let's see what it is. So yes. So now that brings us to starting to define what work is basically. Now work is something which is like it's like an effect that we define on an object. And basically that effect is that when there is a force which acts on an object and it causes the object to get displaced, then we say that there's been some work done on the object. So there, as you can notice by when I say these these things, I'm actually already implying some necessary conditions for there to be work done on an object. Now, if you notice, I said there is a force which acts on an object to cause displacement. Right? ये तीन चीजें मतलब उस force से displacement चाहिए, and only then can we say that there's been some work done on an object by that force. Okay? So why that's important is because sometimes we have forces acting on an object, but those forces may not be causing any displacement. Then in that case, there is no work being done on an object. So let's just see to understand this necessity of these three things together. Let's look at a few examples. So let's first look at a few examples of work being done, basically. So for example, there's a horse which is pulling a plow, right? So वो horse pull कर रहा है इस object को, so that's why there is work being done. Then if you're pushing the grocery cart in the shops, then आप लोग you're applying a force, and that force is causing displacement, which is why there is work being done, and so on. ये दूसरी भी, these are examples in sports of the same thing. So for example, when there's an athlete who is throwing a short put, then the athlete has applied a force, और उस force की वजह से displacement हुई है, right? So there are all these three things that we require: force, displacement, and cause, for us to be able to say that work's been done. Now, I just want to check that you've got this understanding completely clear. We need those three things. We need a force to cause motion, to cause displacement, to be able to say that that force has done some work. So let's see, I've got a few examples up here, and you guys tell me whether there's been some work done or not. So I've got I'm standing here, obviously, and I'm just pushing the blackboard right now. Or Zaire, as you can imagine, I'm not a Iron Man. I'm not an Iron Man, right? So I can't really, the wall's not going to move when I'm trying to push it. So you guys tell me, do you think that there's any work being done by me when I'm pushing the wall, but it's not moving? Please reply in chat. I can see your chat responses. Ahmed is saying no work, no work. Okay, why is there no work? Just always pop in the explanation as well. Because there is no displacement. Excellent. So that force is not causing any displacement, and hence there is no work being done. Flat out, right? The force must cause displacement. Are three keywords. Force must cause displacement, and there is no displacement here. Okay, next example. There's a book that falls off a table and free falls to the ground. This is a bit interesting. Is there a force acting on it? Let's first think about that. And if so, is there displacement being done because of that force? Yes, there's a force of gravity. Rajil, so बस yes, okay, force of gravity. और वो जो is the displacement being caused by that gravity? मतलब is there work being done? Exactly, Ahmed. Good. Yes. Yes. सब लोग इस केस में सब बस yes कह रहे हैं और पूरी तरह explanation नहीं दे रहे हैं. मैं 3-4 दफा yes कह देता हूँ, शायद ये फिर पूछना बंद कर दें. Yes, it's the weight which is causing the displacement, right? And something is falling, it's being displaced, that is being caused by gravity. So exactly right, there is work being done by gravity to cause that particular motion. Okay, now next. There's a waiter carrying a tray full of meals above his head with one arm straight across the room at constant speed. So, मतलब ये कि there's a normal force which the waiter is applying on the tray, which is acting vertically upwards. One arm straight. Let me draw out my waiter. This is the tray full of, you know, and then he's moving in this direction. Very good. Ahmed, very good. Why is there no work on the tray? But the person is okay. Aliza, why? Tell me why.
There is no displacement in the direction of force.
यस मैम, जहाँ को वो फोर्स लगा रहा है वहां को वो ट्रे वहां को मूव नहीं कर रहा, वो ट्रे दूसरी तरफ मूव कर रहा है. इसका मतलब है कि वो जो पर्सन है वो ट्रे पे वर्क नहीं कर रहा.
अच्छा जी, वेरी गुड, थैंक यू. ये जो भी थे, थैंक यू फॉर द कम्प्लीटली वेरी प्रिसाइज फुल आंसर. बट प्लीज कमेंट्स में लिख दें ताकि बाकी लोग भी साथ साथ चले. नहीं कोई बात नहीं, क्योंकि वो लोग कमेंट भी तो पढ़ ही सकते हैं ना. सो perfect. So everybody is thinking in the right direction, and your colleague just said it completely right, that there is a force acting, but there is no displacement in the direction of the force at all, right? The force is acting upwards, so the force is in this direction, whereas the motion was, or displacement was, at 90 degrees to it. So this force had not caused any displacement. So when they're at 90 degrees, then of course उस force की direction में कोई displacement नहीं हो रही, and there is no work being done. Perfect. And then finally there's a rocket accelerating through space. I think this is pretty straightforward, right? So maybe actually there is something to think about. Then there must be some sort of a thrust force acting on it, which is causing that acceleration coming about because of the burning of the fuel. And that is basically when it's accelerating and displacing in some sort of component because of that force. So there is going to be work being done by that force, be it at least there's going to be some component, that's something for sure that we can say. So that is going to be causing some displacement through space. So that's good. So everybody's got this sorted. So we've got the hang of when work is being done. We've seen that there are these three things which are required. Now let's just take a look at how do we find the work done by a force. So as we've just said, we need three things, right? So a force must be causing displacement, right? So that means that if we have a force acting on a particle, something like so, F, and we know that it's moving along this trajectory S, then if we can just, so if it's moving along this direction S, then I know okay, when it's just moved like a small distance, let's say dr, वो यहाँ से यहाँ चला गया है, या फिर in terms of the magnitude of dr, मैं approximate कर लेती हूँ my arc length say, so ds. So when it's just moved a small distance ds, and if I find what was the component of the force which caused this motion ds, then I can find the work acting on it. So if you're considering just a small change going from here to here, then our distance that it's moved is, let me just write that. So the work done, the small work done, I'm going to represent by U, or actually let me repeat that. So the work done I'm going to represent by capital U. We'll see shortly why I'm doing that. And then because I'm just talking about an incremental displacement, I'm talking about an incremental change in its position. So I'm also just talking about an increment of work being done by the force. So that's why I'm looking at du. Or what would that du be? That is just the product of the force and the displacement it causes. In this case, what's a little bit easier is to notice what displacement is being caused. As I can see, oh, in vector form it's moving by dr, but abhi pehle maine sirf scalar zara, let me just write down the scalar version because it's easier to know. So when it went from here to here, the displacement hui ds. So I've got my ds right. But now, as we just had discussed, work is done by the component of the force in that direction of the displacement. So I have to be very careful to notice कि अच्छा अगर उसके ऊपर resultant force या फिर जो भी force थी that's acting in this direction, F as shown by this arrow, then it's not just F times ds, it's the component of F which was causing this motion, which if I'm projecting with this angle theta is clearly this one is going to be F cos theta, right? Because that's the component of the force in the direction of the displacement that occurred. So my small increment of work being done is F cos ds. Now I hope maybe आप लोग अभी भी vector analysis or vector calculus कर रहे हैं. I think you guys are a little bit familiar that when you have this something like this, F ds and then cos theta, this is actually the dot product between the cos theta. It gives you the projection in the direction of the two vectors, right? So that actually gives us the dot product of the two vectors which are there. So this F cos theta and then ds is actually just the dot product of F with the small increment or small displacement in vector form. So here I have my force as a vector and my dr also as a vector. ये I'm assuming कि आप लोगों को ये याद है कि ये cos theta जो है वो projection होती है of the vector in our time. लेकिन अगर किसी को नहीं याद, so we can think about it. I hope कि मेरी drawing थोड़ी उससे clear हो जाएगी. So this is my f, and let's say that this was my dr, right? And then this is the angle theta. So जो my dot product, if I take the dot product between these two, f and then dr, this gives me basically, it's sort of like the multiplication. It's the projection of f onto the direction of dr, and then they're being multiplied together. अगर मैं उसको स्केलर वर्जन में लिखूँ ना, तो मैंने अभी डॉट प्रोडक्ट का यूं मतलब होता है ना कि वेक्टर्स की आपस में क्या प्रोजेक्शन है और प्रोडक्ट ऑफ द प्रोजेक्शन. इफ आई जस्ट राइट दैट वेक्टर थिंग जो मैंने अभी प्रोजेक्शन की बात की है डाउन इन स्केलर फॉर्म, देन आई कैन सी दैट दैट इज एक्चुअली उसकी प्रोजेक्शन क्या है. इट्स एफ का कंपोनेंट कॉस थीटा. तो एफ का कॉस थीटा बीइंग मल्टीप्लाइड बाय थीटा. But here these things were vectors, and here now they are just the magnitudes or just the scalar version. So this f is the magnitude of the force, cos theta is the angle between, right? So that's why I can go from that when I have a force f acting on a curve, on a particle that's going in a curvilinear path, then the incremental force being incremental work being done on the object as it moves some incremental distance dr is just given by the dot product of the force and the incremental. Now, just checking, is that clear to everybody why I've got this dot product here?
Yes, ma'am.
Okay, thank you. So, now we've got the dot product part cleared. So let's jump to looking at, this was just looking at the incremental work done. Now, of course, imagine I want to find the total work done as it moves along the entire path. Then what do I need to do? I just need to sum up all the incremental works, which जब आप incrementals को sum करते हैं, that is basically the integral of in the sort of the incremental work, right? So then if I'm going, let's say, from here to here, जहाँ पे पहले मेरा R1 was something, पहले I had my R1, and then I go to a different point in the path, somewhere here, then here my R is R2, position vector. Then my dr is basically, we integrate over dr, this dot product, as our R goes from these two limits of R1 to R2. Thus, this then gives me my total work being done on it. And so I'm going to call it the total work, U, being done as I go from position 1 to position 2. Right? So this would be the work done on the object by this force F as it moves along the path and goes from R1 to R2. Okay, so just this is actually pretty important. I don't know why I forgot to highlight this or put a color around it. But do commit it to memory if you guys can. It's the total work done is basically the force dotted with the incremental distances, drs, and then integrated over the position. Okay. So let's look at a few versions of this expression. So for the case, let's say when we have where the force is changing on the object, right? So how I want to consider that is to go back and look at it in its scalar version. So scalar version में I had written down that my force का मुझे projection चाहिए. So I need my f cos theta, and then again, as I said, my scalar position just along s कर रही हूँ अगर. So that's why I'm integrating ds S1 to S2. Okay, so in this case, of course, if my force is changing, then it could just mean that it's some function as a position of S, right? मतलब ये कि जब मैं f cos theta को plot करूँ against S, f cos theta को against S plot करूँ, then I'm getting some function. Then of course this integral is what? Someone tell me कि ये graphically, what would this integral be?
Area under the graph.
It's the area under the curve. Ahmed is so bored with this question. He's like, thoda sa to higher level puch le. This is too easy for me. Yes, indeed. So this is when it's a function, f is changing as a function with respect to the position ds. Then it's just given by the area under the graph of f cos theta against s. Okay. So either we can just use a graphical method to find it, or if we know what the function f is and how it's changing, then we can just input that in here and integrate it using arithmetic. Right? Now let's consider also, okay, what if for another case that f cos theta is actually just a constant? Then if it's a constant, then it would look something like this, right? So f cos theta against s would just be constant value. And if that's the case, then let me just assume that मेरा fc cos theta. Then the area under the curve is just the area of this rectangle, right? So it just is, u would just become, the area under the curve would just be what? Anyone? You can write it down in chat because it's not, I don't think it's too difficult. When the force is constant.
Delta.
Sorry?
Ma'am, FC cos theta into delta S.
Exactly right. FC cos theta, just the constant force being multiplied. So the area of the rectangle, right? So जो उसकी height थी FC cos theta multiplied by its length, which is delta S, or in other words, just S2 minus S1. So it simplifies it, right? So there we have to be a little careful just to keep an eye out. Okay, what exactly is f? And then just if it's a constant, then we can simplify it significantly. Whereas if it isn't, then don't forget that it actually does involve the integral. क्या असल में होता है कि लोग ना ये बात भूल जाते हैं कि it's not just the straightforward product of f and just the distance move. It's actually the integral. So it is f dot dr integral. Okay? That is what u is as we go from one. Perfect. Now there's also actually a few other things that we need to think about, which is first of all that if you look carefully at this expression for the work done between 1 and 2, you can see there's a dot product between two vectors, the force vector and the change in position vector. Now I think from again your vector calculus, you might recall that the dot product between two vectors gives us a scalar value. So that's implying to us that the work done is actually a scalar. Okay, so this is pretty important. You just get one sort of a value, a scalar value for the work done by a force. And then there's also another thing, that this dot product, that does not sort of give us any conditions for the sign of the scalar, such that our work done can actually be positive or negative. So it's positive if the force and the displacement, or F and dr, are both in the same direction. But if in their opposite directions, then the work done will be negative. So this is something to keep in mind, that the work done is a scalar with a positive or a negative sign. And then finally, again, as we discussed before with the example of the waiter, that if the force and the displacement are perpendicular to each other, then of course unka the cos theta, cos of 90 degrees, cos of 90 is 0, right? That is, there is no projection of the force in the direction of the displacement, such that then the work done by that force is 0. Okay? So if the force and the displacement are in the same direction, then it's a positive scalar value. If the force and the displacement are in opposite direction, then it's a negative scalar value. Whereas if the force and the displacement are just perpendicular to each other, then we get 0 work done. Perfect. So I hope these things are a bit clear. Good, Osama, thank you. So let's have a look at an example of a case where you do sometimes. Sorry, Azan. I'm just going to take a little break for Azan, please. Okay, so let's look at an example of the work done for a case when we do need to be a little bit careful about the signs. Now, which is basically the work done by the force of gravity or the work of weight. So let's think about this. So as I go from, let's say, position 1 to position 2, then again my work done is just going to be the product, the dot product between F and dr. So let's write those things down. So because there's a dot product, I'm just going to simplify this very, let's see what it comes down to basically by using vector analysis. Okay? So I'm not jumping to some conclusions directly कि okay नहीं मुझे पता है force की क्या direction है मुझे पता है क्या direction. I just want to see कि what I intuitively think, does it come out to be that or not, using actual arithmetic analysis. So my force is just going to be the weight of the object acting in the minus y direction, right? So that's why there's a minus wj. If I'm using my x, y, z, I, j, k basis vectors, so my force is minus wj. Now, as it goes from S1 to S2, then it's going to have changes in each of its x, y, and z components. Right? As we're performing the integration, we actually do need to take a look into each of the dx's, dy's, and dz. अब वो dx जो है वो I direction में, dy जो है वो j direction में, dz जो है वो k direction, right? So that's why this is what my dr vector becomes. Each I, j, k component के in. Now I take the dot product with the weight. The dot product, so I think कि आप लोगों को ये याद होगा कि वो it's the product of the same product of the components in the same direction. मतलब ये कि अगर इसका I का component होता तो वो दोनों I's multiply होते, plus the J's would get multiplied, plus the K's would get multiplied. Now in this case, I only have a J component of the force, such that I'll only get this minus W being multiplied by the J component of the arc, which is dy. So I just get minus W dy integrated over, of course, अब वो dy की integration रह गई है खाली. So y is changing as I go from S1 to S2, from y1 to y2. So it just becomes the integral of minus W dy go from y1 to y2. Now the weight is constant, तो फिर हमारा वो constant force वाला case हो गया, and such that I get minus W multiplied by y2 minus y. Okay, so in other words, I could also write down this y2 minus y1 as my delta y. So the thing to notice here is, if for whatever reason now if it's acting under just the action of the weight, it's going to be moving down, right? So that's why this delta y itself, because it would decrease, this delta y would have a negative impact. And hence why the weight and the delta y would be both negative, or they're both acting in the same direction such that you get a positive work done. You can sometimes sometimes अगर कोई और भी उसके ऊपर force act कर रही हो, या for example is driving up or something, then the weight is still acting on it, but the delta y would be moving upwards. So actually that wouldn't work because that's not the work being done by the weight. I apologize. But just my point was that when we figure it out arithmetically, we get a minus in there. But that's only because this delta y itself, it's something that we have to be careful about, because this is the change in the y position, which if it's acting under the influence of the weight, it's going to be acting downward. Okay? So we would still get a positive work. Okay. So I'm a bit unsure what this means. If delta y is upwards, the work is negative, so the weight force always acts down. Yes. But let's see, maybe we'll encounter an example when that happens, that the weight is acting, but it's still moving upwards for whatever. Okay, so just be mindful that you have to be very cautious about the signs of the force and the displacement being caused. Yes.
मैम
हाँ जी.
मैम एंगल जो है वो 180 डिग्री हो जाएगा ना, तो उसकी वजह से cos 180 नेगेटिव का साइन आएगा उस वजह से.
तो फिर वो वापस पॉजिटिव हो जाएगा ना, राइट?
यस मैम.
तो that's what I was saying.
मैम लेकिन वो delta y is a word, the work done is negative.
Work done is positive.
मैम ये लाइन लिखी हुई है ना इसमें, work done is negative.
हाँ जी.
ये कि मतलब जब डेल्टा y अपवर्ड है तो वर्क डन नेगेटिव है ना, क्योंकि डिस्प्लेसमेंट और फोर्स के दरमियान एंगल 180 है और cos 180 नेगेटिव आएगा, तो इसमें ये वर्क डन नेगेटिव होगा.
बिल्कुल बिल्कुल ठीक कह रहे हैं आप. यस, मैं सिर्फ यही पूछ रही थी कि ऐसा केस कब होगा कि वेट एक्ट कर रहा हो और उसका डेल्टा वाई ऊपर की तरफ जा रहा हो.
मैम वैसे स्प्रिंग के केस में तो होता है रिस्टोरिंग फोर्स और डिस्प्लेसमेंट ऑपोजिट डायरेक्शन में होते हैं.
अभी हम स्प्रिंग पे आने ही वाले हैं, लेकिन स्प्रिंग इज नॉट द सेम थिंग एज अ वेट. देयर आर टू कंप्लीटली डिफरेंट थिंग्स.
नहीं मैम मैं वैसे ही बता रहा हूँ कि फोर्स और उसमें डिस्प्लेसमेंट तो ऑपोजिट डायरेक्शन में होती है.
हो सकती है. अच्छा ठीक, यू मीन कि उसके ऊपर किसी और वजह से कोई और फोर्स भी एक्ट कर रही है और वो मोशन कॉज कर रही है डेल्टा वाई का, लेकिन फिर भी जब वेट तो एक्ट कर ही रहा होगा ना उस पर. ओके, फेयर इनफ. यस yes, thank you. So for whatever reason, if delta y is upwards, and the weight is downwards, then of course we will get a negative work done by the weight. So which brings us to this thing of the work of a force, work of a spring, sorry, which जो आपके colleague अभी mention ही कर रहे थे कि उसकी वही एक example है जिस case में displacement किसी और direction में हो रही है और force is acting in the opposite direction. And why that's the case? For example, if you just look at a spring, let's think its unstretched position was this one. So when it's an unstretched position, then it has no force, no restoring force acting on it. But let's say if I've now pulled it to a already to a displacement s, and then I further displace it to a ds, और वो होगा क्यों? क्योंकि मैंने for whatever reason I would have moved it in the positive direction. Then there is a restoring force acting on the particle which is inwards, right, or to the left, because the spring is under now tension. So it's trying to come back to its original position. Now in this case, our Fs is acting in the opposite direction. So if I'm defining my positive direction like so, let's say मेरी x direction is positive, then I can actually see that my ds is to the right, so it's positive, but my force Fs is negative. So in this case, as I go from two different positions of the stretch spring, let's say पहले S1 था और अब वो S2 तक आ गया, पहले इधर था और अब वो इधर तक आ गया, S1 and S2, then the total work done in that case would be the integral going from S1 to S2 of the product of minus Fs, because it's acting in the negative direction, multiplied by ds. Okay. Now, most of the time we have a linear spring, right? Linear spring means that we know that it has a force against displacement, force against displacement diagram, which is straight line, linear, with a gradient of k. That's that. The equation could just be written like so: Fs is equals to Ks, where S is this distance from its unstretched position. So I can substitute that in here for my restoring force. Such that I then have the minus is right there. But what was the force? It's K times S. And now, of course, this is just an integral in S, and I can integrate it. So, because S already was here, then S की power raise हो जाएगी and then divided by the new power, such that it becomes minus of, minus y रह गया, half K, whatever the new position is, S2 squared, minus half K S1 squared. Right? Which, if we think about it, what it was in this Fs against S diagram, this is actually the area under the curve again, because Fs जो है वो हमारी Fs ही हमारी Fs cos theta है. It's the area under this curve, but with a minus. Okay? It's the negative area. Because Fs and S are in opposite direction. Okay. Yeah. So just pointing out कि ये जो expression मैंने यहाँ लिखी है, this is this area. जब आप S1 से S2 जाए, right? The area of this triangle minus the area of this triangle. Okay. So इसके अंदर भी जिस तरह weight के साथ ना, we have to be a little bit careful. क्योंकि अभी when I was talking about it, I'm talking about the case when I'm sort of causing the particle to move to the right. Then as soon as I let it go, right? As soon as I let it go, then again उसका S1 और S मतलब वो पीछे की तरफ जाना शुरू हो जाएगा. Such that in that case, when you will work it out, the the work done would become positive. So sometimes basically we have to be very careful about the directions of the forces and the displacement. Or I'll explain to you in just a little bit why it's important to be careful about the sign. just give me 1 second. उससे पहले spring से related थोड़े से और points. Number 1 point is that I just talked about a linear spring right now, okay? Because it's a linear spring which has an equation which is F is equals to Kf. Agar if it's some other sort of a spring, non-linear ho, and for that case we have to look at whatever its sort of non-linear profile is of the restoring and use the area under the curve to help us find out. If the restoring force was causing displacement in the same direction, then it's directly, this is the positive area under the curve. Lekin agar the motion is being caused against the restoring force, then it's the negative of the area under the curve. Okay, but for the case of the linear spring, was straightforward. Half ks2 squared minus half ks1 squared. All of it is then negative. The expression to use. Okay. Yes. Yes, exactly. So this is important. Yes. So, I think you guys won't make this one. The work of a spring is not just the spring multiplied by the distance at some point. So it's not just ks multiplied by s. Okay. There's a because of the area under the triangular areas under the curve, उसकी वजह से there is a u122 is half a s2 squared minus half a s1 squared whole negative. If then fs and s are in direction. So do be careful about the minus, so the halves in here. They're not just ks. Yes, just again, the sign needs to be checked. So if the displacement is occurring against the restoring force, then it will be a negative work done. If the displacement is occurring in the direction of the spring force, then it's a positive work being done. But now let's move to why that's important, which is basically that we move to the principle of work and energy. And slowly here you will see that actually when we're performing, I'll describe to you what the principle of work and energy is, but in this thing, what we end up doing is that on a particle, often you will have loads of different forces acting, of course, and sometimes we're going to need to find the total work being done on. Now, this is why the signs of the work done are so important. Because of course, ye to sare work done are just going to be scalar quantities, right? Now, when we're summing them together, then whether that scalar quantity was a negative or positive becomes important, right? So that's why for the case of the spring force, for the case of the weight and so on, we have to be careful that individual u1, 2 jo hai, unka sign kya hai, so that when we find the summation, we actually get the correct sort of total work being done on the object. Okay, so to see where the summation comes in, we need to look at the principle of work and energy. So let's jump into it. Now this is going to involve a little bit of manipulation. I'm pretty sure that some of you are already familiar with this. So I'm just going to start off just by asking, so what do you guys think the principle of work and energy is? Could someone please raise their hand? Principle of work and energy. नाम से ही आपको क्या लग रहा है? जी प्लीज शर्जील आप ही बता दें चलें ऐसे कोई और अगर होता क्योंकि शर्जील you answer pretty often. Go on Shirjeet.
The amount of work done must be equal to the change in the energy.
Excellent. Yes, exactly right. So the principle of work done is saying that the total work done on the object must be equal to the change in the energy of the object. That's the principle of work and energy. जितना वर्क आप कर रहे हैं किसी चीज के ऊपर उतनी ही एनर्जी उसमें स्टोर होनी चाहिए. But we all sort of know this just because of sort of conservation of energy से आ रहा है. But let's see कि हम अपने ये kinematic और kinetic analysis को use करते हुए कैसे उसी result पे पहुंच सकते हैं. Now to do that, consider that I have a particle, this one right here, which is going in a curvilinear path. curvilinear path, okay, and it goes from the position S1 to S2. और अभी वो total S1 S2 से जाएगा, लेकिन for now I'm just going to look at a DS, incremental change in its position. Now I know when I look at it in my N and T coordinates, I'm going to know that it's going to have a resultant tangential force acting on it, which is Ft, and a resultant normal force acting on it, which is summation Fn. Now, उसकी जो displacement ds हो रही है, the incremental displacement, that is a force in the tangential direction. Okay, नहीं? So let's start to think about this very slowly. So पहले let me just get up my जो kinematic equation of motion, that is in the nt coordinates, but also let me just, क्योंकि मैंने अभी बात बोली थी ना कि displacement जो है वो सिर्फ tangential direction में होगी, इसलिए अभी ना पहले I'm just going to bring up my equation of motion in just the tangential coordinate. Then I know that the equation of motion is the resultant force in the tangential direction, that will be equal to m times the acceleration in the tangential direction. Now we all know कि ये जो AT था, AT जरा सा special था. AT की expression क्या होती थी? That was just equal to the change in the magnitude of velocity, which is v dot. Because it was just this AT is equals to dv by dt, we had noted कि ये tangential acceleration तो वही straight line motion वाली expression लेती है, which means इसके ऊपर सारी वो जो हमने तीन original straight line motion वाली kinematic equations use की थी वो apply होती है. That is, this third kinematic equation also applies on it. तो मैंने v dv लिखा है. AT ds is equals to v dv भी apply होता है AT के ऊपर. So that's what I'm going to do. I'm going to substitute the expression for AT, because this then becomes v dv divided by dx. I'll pop that in here. v dv divided by dx. और अब देखिए फिर what I'm going to take my ds to the right hand side, but then I'm going to take it to the left hand side, such that I'm then just going to have ft multiplied by ds on the left hand side, and on the right hand side I'm going to have mv dv. Now both of these are, there's a ds here and there's a dv right here, so I can integrate them with respect to my with respect to whichever the variable was on which the differentiation is happening. So this then becomes an integral of over s, whereas the right hand side becomes an integral over v. Now is the interesting part. Surely अभी जो हमने सारा work के बारे में description देनी शुरू की, उससे this is something which is familiar to us. Isn't this the work being done by the tangential force on this particle as it moves along the path? That's exactly what it is, right? याद है ना आप लोगों को? U was summation F dot dr. या फिर in other words it was F cos theta ds in the scalar version. Now, for our case right now, this F cos theta जो है, क्योंकि मेरी ये resultant force, it can be decomposed into its tangential and normal parts, right? So this F cos theta is Ft. Fr अगर u था और ये मैं theta ले लूँ, projection of the resultant force onto the onto the direction of the displacement, the tangential direction. So this F cos theta is Ft, and hence why I just have Ft ds. So this expression on my left hand side is actually the total work being done, and then there was a summation right there, the work being done on the on the particle as it moves from 1 to 2. And the right hand side, उसको भी मैं integrate कर सकती हूँ. And this integral, because ये तो variable v है इधर, and this is being integrated over with respect to v.
मैम
जी.
मैम हम हमेशा ये क्यों कहते हैं कि वर्क डन ऑन एन ऑब्जेक्ट इज इक्वल टू चेंज इन इट्स काइनेटिक एनर्जी? पोटेंशियल एनर्जी नहीं हो सकती चेंज?
Potential energy नहीं हो सकती या हो सकती है, अभी मैं उस पर बात देख सकते हैं. Just give me 1 second to complete this, and then I'll just discuss it.
ओके मैम.
Okay. So as one of your colleagues has just spotted already कि ये right hand side को जब मैं integrate करूँ MVdV को, then I'm getting these two terms, half MV2 whole squared minus half MV1 squared. और ये चीजें are eerily similar to what I know to be the kinetic energy of the particle at position 2 and at position 1. मतलब ये the total work being done on the particle is actually equal to the change in the kinetic energy of the particle as it goes from as it moves between position 1 and position 2. I'm coming to your question in just a second. ये थोड़ी सी ये slide को So be careful here. हम लोगों ने कोई conservation of energy का कुछ वो नहीं लगाया था. We just been हम अपने book kinematics वाली expressions को use करके सिर्फ arithmetically इसको manipulate कर रहे थे. Or the reason why this conservation of energy was popping up was because actually this equation of motion जो है ना, that is the thing that we've been doing last week. The equation of motion. That is actually also just it's actually equivalent to this principle of work and energy. और इसी वजह से उसी से हम इस पे भी आ जाते. So all of these different things when we talk about them, the conservation, the second law of motion, and so on. As you remember, we talked that this is only applicable when we have things which are sort of, when we're talking about classical mechanics, right? तो वो दोनों एक ही चीज को फर्क तरीके से कहने की बात है, but they all are actually equal, and that's what we've just been seeing right here as well. And starting from our equation of motion, we can actually lead to our sort of a principle of or conservation of energy or the principle of work. Right, there are a few things in here which I also want to clarify before taking the question, which is the neatness of now the principle of the work and energy part. इसके अंदर हमारी accelerations नहीं आ रही. That is, sometimes the point is just to solve various different kinetic and kinematic problems, right? So depending on what information we have, then we choose which one is the most efficient method. So if हमारे पास कोई ऐसा particular problem हो जिसमें हमारे पास velocities or displacements known हो, then it's a good idea to use our principle of work and energy, because इसके अंदर वही चीजें feature होगी. इसके अंदर it's the force, the displacement, and the velocity of the particle which take a part, right? So, in this sort of a case, it would be better or more efficient for us to use this principle rather than to use our equation of motion. Achha, one more thing that I want to point out still from our kinetic sort of को देखने की तरफ से, which is के only the tangential force is playing a part, not the normal force. Now, why is that the case? Number one, तो ये कि if you go back to looking at our F dot dr, उसके अंदर this force, the resultant force की projection in the direction of displacement is the tangential force. तो ये देखो ना, इस FR का component ही वही वाला है, मतलब ये delta F ही तो है जिसकी वजह से ds हो रहा है. Or, and to put it even more clearly, this normal force was causing the change in the direction, but it wasn't causing any displacement. There is no displacement in the direction of Fn such that there is no work being done by the normal force, and it does not feature in our principle of work and energy. And you only have this summation U12 के अंदर you will only have summation of the integral of the tangential force along the path. Okay, so do think about this as well as we go through this. Right, now let me come to what your colleague was saying, which is कि इसी expression को अगर आप और से देखें, so you can probably spot that these terms on the right hand side are actually the kinetic energies of the particle at position 2 and at position 1. So let me represent the kinetic energy as T, and then hence this becomes T2 minus T1. When I rearrange this, then it also becomes this expression right here, which is that अगर हम किसी initial kinetic energy से start off करें, and then I do some work on the particle, then that's going to give me the final kinetic energy of the particle. ये सब equivalent हैं, just different ways of representing them. So this is what then it becomes some sort of a conservation of energy type of an equation, right? Another thing to notice here that these summations are the sum of all the work done by the force, right, as it's moving from point 1. So as we had discussed, the work done can actually be either a positive or a negative. So we have to be careful about this. We have to be careful about the sign of the work being done. Whereas the kinetic energies T1 and T2, they are always a positive scalar. Okay, they are never negative. They're always going to be a positive scalar value. Okay, so I think I hope all of this is clear. Now let's take your colleague's question. Okay, ये हम इसके अंदर potential energies को क्यों नहीं करते? Okay. First of all, I want to point out to you that when there's a change in the abhi hum jo we are talking about just kinematic and kinetic problems, right? So हम sort of temperature changes वाली problems के बारे में इतनी detail में हम लोग basically उनको discuss कर ही नहीं रहे, right? This is a dynamics course, not a heat and mass transfer, right? So in that case, whenever there is a change in the potential energy, that is happening because of some sort of a displacement occur. In the case of kinetics, right? So for example, if the person if the body is changing its height because it's acting under the action of the weight, then again वो weight act कर रहा है and causing a displacement. So you can look at this as the work being done on the particle by the weight. To cause or work done is the change in the potential energy, sure, but there's work being done. Similarly, if there's a particle which is attached to a spring, उसमें भी यही बात हो रही है. There's a displacement being caused by the spring, or वो spring की potential energy is being converted into the work being done on it, and so on. So my point is being, okay, for our case in this dynamics course, the potential energies are already incorporated into the work being done on the object. And that's why they are not explicitly being featured. Lekin they are implicitly being featured. Why? Because ये थोड़ा हम sneaky हो रहे हैं इधर. Why? By us choosing to represent the work done by you. Now I maybe some of you are familiar with this fact कि often हम potential energy को ना या U से या फिर कुछ लोग उसको V से भी represent करते हैं, potential energy. तो इधर हम लोग ना work done को उसी से represent कर रहे हैं, just because there is actually a link on the work being done and the change in the potential energy of the part. So that's what I was trying to say.
मैम टाइम हो गया है, प्लीज
कह रहे
क्लास
हो
एंड
हमारे केस में ओनली बिकॉज हम लोग डायनामिक्स हम काइनेटिक प्रॉब्लम्स को एनालाइज कर रहे हैं, उसके अंदर दैट स्टिल बीइंग इनकॉर्पोरेटेड विद द प्रिंसिपल, राइट? सो दिस इज द प्रिंसिपल ऑफ वर्क एंड एनर्जी बेसिकली, एंड इंशाल्लाह फ्रॉम टुमारो we'll just do a little recap of this. ये अभी मैं थोड़ा सा इसको This is just a summary. And then from tomorrow, we'll move to looking at kinetics, but using the principle of work and energy to see how can we directly solve for the forces, velocity, and displacement, even when we have no concern for the acceleration. Right. Okay, so that's it for today. Thank you all very much. Inshallah, see you tomorrow.